Okay, let us consider the general solution of a wave equation. This is the wave equation we have derived, and we solve the equation by making use of the separation of variables. Separation of variables means that we introduce a function, a known function as a trial function, as a product of two functions. Each function has a single variable function, so there's no mixture of two variables in the middle. So if we substitute this trial solution to this equation of motion, this time derivative applies to the function capital T, and the spatial derivative applies to the function capital X, which is a function of X only. Does the function of X factored out and function of T factored out? If we divide both sides by X times T, then left-hand side becomes a function of T only, and right side becomes a function of X only. Because function of T is equal to the function of X, the only possible solution is the both sides are independent of X and T. Although T has time dependence, all of the time dependence cancels by dividing this derivative by the function of T, and X dependence also cancels in this ratio. Therefore, this number is independent of both X and T, and it results in two equation of motion for T and X separately. And because K is not determined, it is a kind of eigenvalue problem. Reorganizing dividing in this simultaneous equation into two pieces, the X variable differential equation and T variable differential equations are separated completely. And this is the same as the harmonic oscillator problem, the second order differential equation, and the solution will be a function of X. The solution of this will be a function of T. And K is the wave number in this problem, and KV becomes the angular frequency omega for the time variation. The boundary condition of this problem is the endpoint, two endpoints are fixed. So we can reorganize this exponential linear combination in terms of linear combination of cosine and sine. If I substitute t equals 0, then beta 1 prime becomes 0. But if I substitute L equals 0, then the sine KL becomes 0. Because of this KL must be a multiple of pi. Therefore, L is pi r divided by the length of the string L. We know the normalized function for this eigenfunction is 1 over square root 2 over L. The result for the time oscillating vector can be copied in here. Here alpha r and beta r should be determined from the initial conditions. For example, phi at t equals 0 and phi dot at t equals 0 are known, then all of the undetermined coefficients alpha r and beta r can be obtained. This is an expansion. This is actually the expansion in terms of the eigenfunction, and this is normal coordinate. Okay. Next, we consider the Euler-Lagrange equation. The vibration on a membrane, we have constructed the Lagrangian density for the membrane problem, and action can be constructed by integrating the Lagrange density function over space and time. Here, this Lagrange density function has the contribution of time-dependent factor that has 1/2 sigma. Sigma is the mass density per unit area, and minus 1/2 gamma gradient square for along the x direction, y direction. And this gamma is related to the tension, and this is surface tension. That means tension for a unit width of a stripe. In order to compute the variation of the action, we have to find out the variation of the Lagrangian density. In general, Lagrangian density must be a function of the generalized coordinate. In this field theory, that generalized coordinate should be the time-dependent scalar field phi. Thus, the variation should be made related to the scalar field. The first contribution is the partial derivative with respect to scalar field phi. And then, as we have computed explicitly, there are contributions related to the partial derivatives of the field. Because the field is a function of time and space coordinates in this two-dimensional problem, time derivative of the field and spatial derivative, this x derivative and y derivative of the field phi appears. Therefore, we should make the variation of regarding the time derivative of the field and the spatial derivative of the field. So the partial derivative of the Lagrangian density function multiplied by the variation of those derivatives. As usual, we re-express this in terms of the time derivative of the variation of field and the spatial derivative of variation of the field. Then it is expressed in terms of total derivatives of this product, and then subtracted by this contribution where the derivative is applied to the one factor. The same is true for the x derivative and y derivatives. The results are given in here. Boundary conditions should be considered. The integration over t is from the initial time and the final time. Integration over x and y are given for the smallest value for this box, and small, and upper bound, lower bound and upper bounds are fixed. So this is in this kind of case, x runs from 0 to L, and y runs from 0 to L. All right. So we do not allow the variation of the field at those endpoints. These three terms are all total derivatives because the total derivative with respect to t, x, and y, if we substitute this variation into here, then these 1, 2, 3, 4 terms should be evaluated. The integral should be done for 3 dimensions, and these integrals, one single integral can be integrated out. After the t integration, this contribution becomes this, and after the t integration, the variation at the endpoint appears. The variation at the endpoints at T1 and T2 vanishes, so this contribution vanishes. In a similar manner, after the x integration, we have boundary conditions to kill this contribution, and after the y integration, we have variation at the endpoints of y. Thus, the total derivatives will disappear eventually after integration. We end up with the variation of the action to be the three-dimensional integral. This linear combination of 4 terms multiplied by the variation of the field. Hamilton's least action principle states that the variation vanishes for arbitrary variation of the field. Therefore, the coefficient must vanish. That is the Euler-Lagrange equation. We substitute the Lagrangian density function into the Euler-Lagrange equation to find that the resultant equation of motion is actually the same as the original one, that is wave equation. We also consider the general solution in a different way. The wave equation is of the form, and the solution of wave equation is always a linear combination of x plus minus vt. Let's see. Let f be a differential function, and we substitute arguments instead of x, but we substitute x plus minus vt. If I take the derivative with respect to x, it is just the derivative of f, whose argument is x plus minus vt. If I take the derivative with respect to time, because of the chain rule, we have over a vector plus minus v. If I do the same job twice, then second order derivative of f with respect to x will be the just double derivative of x, where x is replaced with x plus minus vt. In case we do the same job with time, because of the chain rule, we have over a vector plus minus v squared. So for any arbitrary function, this is always true. So this wave equation, the result is the wave equation allows two different waves. They are identical wave, except that it is traveling forward and backward. We can extend this into 3 dimensions. It becomes Laplacian, and this is the most general form of the wave equation. In quantum mechanics, the wave equation is the Schrödinger wave equation is a little bit different. The main difference is the order of the time derivative. Degree of this order, second order derivative appears in the time derivative for the classical wave equation. In the Schrödinger case, we have a single power, a single derivative. Therefore, time-dependent factor in the normal coordinate is a linear combination of sine and cosine. In the case of wave equation, this is related to the forward-backward symmetry. But in the Schrödinger equation case, we have only a single power, so we do not have a linear combination of exponential I over h bar plus minus et. Instead, we have only single case, which has a negative sign on it, and there is no positive sign at all. All right, wait a second. Next, we consider standing wave. Because the wave equation allows the solution of identical piece, one is moving forward and the other is moving backward. So it is possible to add up 2 different waves where everything is the same except that the direction of propagation is opposite. The resultant wave of those is called the standing wave. We have sine kx minus omega t that is moving forward, and sine kx plus omega t that is moving backward. Here the phase is kx minus omega t, and k wave number k is the 2 pi over lambda, and angular frequency to omega is the 2 pi over period. If we factor this out, k factored out, then it becomes x minus lambda over t period. That is the wavelength divided by period is the phase velocity, v. Superposition of the two waves leads to 2 times a sine kx cosine omega t. That means the spatial contribution and time-dependent part is completely vectorized. So we can understand this is the amplitude with respect to time, but if I look at this function, it is not this is kx minus something t, and this something is 0, so the velocity of this propagation is 0. That means it is standing. It is not propagating to the left or neither to the right nor to the left. It is standing wave. Phase velocity is, let us consider the case we have a wave complex wave with the exponential I kx minus omega t. The argument of this exponential is called phase. And phase velocity is the velocity of wavefront keeping the phase the same. That means the differential of this phase is 0. For fixed k and omega, we have this constraint. Therefore, dx over dt is omega over k. That is called omega over k is called the phase velocity. Consider the wave equation once again. If I look at this wave equation, the propagation speed v is fixed completely. But we do allow the variation of omega and k. For example, suppose that we have a phase velocity of a wave, and we have another wave with a different frequency and different wavelengths, but keeping the speed of wave propagation the same. That means if I have some slight change from omega, then omega prime should be omega plus delta omega, and k prime should be k plus delta k. Indeed, although the speed of propagation is the same, we are allowed to have different omegas, and consider the case, let us consider the case that delta omega and delta k are rather small in comparison with their original value. When the difference appears, difference is allowed, the propagation of the signal is different from the phase velocity, and that is called the group velocity. Let us consider the superposition of two waves with a different omega and different k. Here is an example. We have a first wave with kx minus omega t, and we have another wave that has a different wave number and frequency, and difference is delta k and delta omega. If we factor out the common factor, then we have 1 plus something, and this is something has the dependence on delta k and delta omega. If we pull out the half phase of this, we have 1/2 of delta k added to the wave number, 1/2 of delta omega added to the frequency. And remaining piece is a sum of two exponential with different phase, opposite phase, that is 2 times cosine. We have indeed, if the delta k and delta omega are small in comparison with the original value, but actually this is the average value of these two numbers, k and k prime and omega prime. So this front factor is the average of these two waves. So this one gives a phase. This is the propagation speed of this wave is very similar to, very close to the original wave, and its phase velocity matches to their phase velocities very closely. Instead, the remaining factor has another wave. So this is a product of two waves. Both of them are propagating. And this front factor propagates with almost the same as the original phase velocity. And if they are different slightly, then remaining piece has very much another velocity that is very different from the original phase velocity. Here, the velocity of this wave is delta omega over delta k. Sure, factor of 2 cancels. So this one, we call this one as a phase velocity, group velocity. we can carry out the same calculation using sinusoidal waves, and as a result, we have the two vectors. One vector, this is original wave, and we have another vector. This is another wave with a long wavelength. And the speed of this wave packet moved forward. We can see this one is moving forward, and also this packet is moving forward. This sign, negative sign, shows that this packet, this one is for this packet, so this is moving forward, as well as this phase velocity is moving forward. So there's a great difference between the group velocity and phase velocity. We can carry out the same calculation by making use of the period and the wavelength. This one shows that in the spatial sense, that we just take the picture of the wave at a certain time, then we can analyze the x dependence. And this is the period. This is the period of the wave packet related to the group velocity. The shape is, although the shape's period is half of original period, so that is that has the difference in the x. If we consider this delta k x is 2 pi, then the actual distance between these 2 points will be the x, and actual distance between these 2 points, the 2 nodes, will be the half of x. If I substitute this result into here, this pi over delta k is wavelength square root divided by delta lambda. The detailed calculations are shown in here. Therefore, if we have a small difference in the wavelengths, this is much greater, much longer than the lambda. We say this one is lambda multiplied by lambda over delta lambda, right? So, therefore, original wavelength inside the wave packet, this is lambda, and this one is much longer because this lambda over delta lambda is much greater than 1. This width of the wave packet is much greater than the original wave that generates the phase velocity. Let us next consider the infinite potential problem that appears in the quantum mechanics, because we would like to compare our results for the solution for the wave equation. As far as the spatial component is concerned, we have second order derivative, Laplacian, in the Schrödinger equation. However, the normal coordinate should be different because the Schrödinger equation time dependence appears as a first order linear differential equation, but in the case of wave equation we have second order. Anyway, the one-dimensional, two-dimensional, and three-dimensional infinite potential problem can be considered in this way. And actually, it is a free particle, except that it is a particle wants to move outside of the barrier. The potential becomes infinity. If the potential becomes infinity, the wave function must be 0 because the energy conservation is violated. Therefore, we have infinite potential means we are introducing a boundary condition that all on the boundary and outside of the boundary, the wave function must vanish completely. That means psi equals 0. Separation of variables can be applied to find out the solution. We express the equation as a product of time-dependent and spatial-dependent contribution. And x is again factored into x, y, z components separately as a completely factorized form. Again, we substitute this trial solution to the Schrödinger equation and divide both sides by that solution. Then we have a vector depending only on time. We have another vector depending only on x. Because they must be equal, this one must be independent of both t and x. That is actually the energy eigenvalue. Once the energy eigenvalue is given, then this time-dependent part is completely solved. And unlike the case of wave equation, Schrödinger equation solution has a single exponential complex. It must be complex always. So it is impossible to have sine and cosine. So the phase is completely determined because it's first order differential equation. This time-independent Schrödinger equation is rigid, and because it's actually the free particle equation, potential becomes 0. Except that when potential is non-zero, wave function is completely vanishing. So solution of this 1D problem is actually potential should be 0. This is a linear combination of exponential ikx and minus ikx. The boundary condition restricts the solution to be square root 2 over L sine n pi over Lx. Here n must be 1, 2, 3, 4, 5. This is a natural number. Suppose we have n equals 0, then the wave function itself disappears. It is 0. Once the wave function is 0, the probability of finding the particle is 0. Therefore, we do not consider that trivial case. In addition, once this spatial oscillating part is completely determined in terms of the eigenfunction, psi n, we can compute the k value, wave number is determined because this wave number is determined as n pi over L. This is quantum number. That one can be substituted in here to find the energy of this particle. Once the energy of particle is determined, time oscillating vector is determined. And in here, this Cn times exponential time-dependent vector is analogous to the normal coordinate. And this is eigenfunction, right? In the case of two-dimensional problem, we can apply the same method. Substitute the spatial component in here. Substitute to this equation. Divide this equation with the x times y. We have sum of x-dependent function and y-dependent function equals constant. That means that these are all constants. Therefore, this one depends on x only, then this one depends on y only, and this one is a constant. And because the sum of these two is constant, they must be constant too. Therefore, we introduce different eigenvalues for minus alpha squared and minus beta squared, whose sum is minus 2m over h bar squared energy. We end up with the second order differential equation for x and y. They can be solved as a linear combination of exponential I alpha x and exponential minus I alpha x. In the case of y, we have similar linear combination. The boundary condition for this problem in the box means the x wave function vanishes for both endpoints. That brings in the eigenfunction sine n1 pi over L1x. And y has a similar function, which has L2 dependent. Because the energy eigenvalue is completely determined by alpha and beta, because this one is alpha, n1 pi over L1, and this one is beta, n2 pi over L2, we have determined the energy eigenvalue for this box potential. Again, because the eigenfunction is a product of x eigenfunction and y eigenfunction, and both of them are signs, this integer must be positive definite. If I substitute n, either n in n1 or n2 equals 0, the wave function disappears. It just becomes a trivial wave function 0. The time oscillating factor is determined by these two quantum numbers. Again, if we introduce a negative integer that is completely linearly dependent on the positive eigenfunction, so negative is not to be considered. There's no difference at all. We can further generalize the method to the three-dimensional case. Then the x, y, z dependent part is completely determined as alpha, beta, and gamma eigenvalues. Those alpha, beta, gamma eigenvalues are completely determined by n1 pi over L1, n2 pi over L2, and n3 pi over L3. This is the product of eigenfunctions, and energy eigenvalue is completely determined as h bar squared over 2m and this piece. The normal coordinate in this case will be this one. Okay. So let us consider the case, the extension to the membrane vibration in the classical mechanics. Separation of variable can also be applied to this case, and the boundary conditions are exactly the same as the quantum mechanical box problem. The boundary condition is coming in. Again, we substitute trial function, x dependent, y dependent function, and time dependent function. Substitute this phi into the wave equation. We have time dependent piece, x dependent piece, and y dependent piece. Again, we introduce eigenvalue alpha, beta, and gamma for time and x and y dependent piece. This brings in three separate completely decoupled differential equation for x, y, and z. Alpha, beta, and gamma are eigenvalues for those problems. Again, the boundary condition determines the wave numbers for x and y separately. In the case of time-dependent piece, gamma is not an eigenvalue, but gamma squared v squared. Because of this v, gamma squared v squared is the eigenvalue. So gamma v is sure, this gamma is a number that is different from this gamma that appears as the surface tension of the membrane problem. As a result, eigenfunctions for x, eigenfunctions for all y are completely determined, and normal coordinates can be determined in this way, where the frequency of the wave is determined by this one. Now, we can further generalize this method to the three-dimensional wave. In the three-dimensional wave, we slice the space into bands with the non-vanishing cross-sectional area, just like the square pipe. Again, we need a field that time-dependent field that depends on the time and positions. And x, y, z are continuous variable determining the position in the space. But in case we are solving the problem in this discrete way, we could have introduced three indices for the lattice: x lattice, y lattice, and z lattice that are all indices are I, j, and k. The mass of each part in this situation the mass m of each cube. If I slice this object into the cubes, the mass m for the discrete case can be understood as this one. And mass and the width of x, y, z, edge length of the edges, and x, y, z direction will be the d, and we take the limit. D goes to 0. Then we can introduce the density, volume density of mass density per unit volume is rho, that is m over d cubed. The volume of this cube is d cubed. And we also need to consider the volume effect. If it were a string, tension was enough to consider. But if it was a membrane, we sliced the membrane into stripes, then we had to consider the width effect. That means surface tension, that is tension divided by unit cross-sectional width. In this spatial distribution, tension per unit area is necessary to describe the problem. That is called the Burke modulus. Burke modulus is the tension per unit cross-sectional area. Let us come back to the original equation motion. We have three indices I, j, k, m mass times acceleration of each object at the bin, and I, j, k, is the sum of the three pieces. This one is the force due to the wave motion along the x-axis, along the y-axis, and along the z-axis. The change along the x-axis is considered as keeping J and K the same, but varying this i's. In the middle is the contribution for the wave along the y direction, that is keeping I and K the same and varying J indices. And the third one is the component of contribution of Z distribution, that is Ij are kept the same, only the K is varied. This three term can be reorganized as a difference of difference. That means K plus 1 minus K, the I plus 1 minus I, and I minus I minus 1. If I insert the factor d in the denominator, this one becomes a first order derivative, and the difference will give the second order derivative after we divide this one into add additional d in the denominator. That is, we have divided this with the d squared. In addition, in order to express the Berg modulus, we need to divide area, that is d squared. Because original vector has a single power of d, we have introduced a triple power of d. So d cubed must be multiplied to have the equation the same as the previous one. The m is now replaced with rho times volume. There's a triple d's. Okay, rho times a d cubed. That is dx, dy, dz. Okay. Therefore, we end up with the equation of motion to be rho times a double time derivative of the field and volume element. This is kappa, Berg modulus, and Laplacian of time-dependent field and volume element. If we cancel dx, dy, dz and divide this both sides with kappa, we end up with the equation of motion. The resultant equation of motion is 1 over v squared double time derivative subtracted by the Laplacian equals 0. The speed of the wave propagation is the square root kappa over rho, where kappa is the bulk modulus, that is tension per unit cross-sectional area, and rho is the volume mass density per unit volume. Now let us construct Lagrangian. First, we write the kinetic energy. Kinetic energy is 1/2 mass times velocity squared. We divide m with the d cubed multiplied d cubed in here. That means m over d cubed is the density per unit volume, and d cubed is actually the differential of the volume. Q dot is to be replaced with the time derivative of a field, and we square. The summation can be in this continuum limit. The summation is to be replaced with the integral. Therefore, this is 1/2 rho time derivative of the field square integrated over space is the kinetic energy. Potential energy can be computed in this way. The force on a bead, the IJK beam, is mq double dot. This is double dot. And tau over d, a difference. Tau over d, difference for I, j, and k variation. From this, we have obtained the 1/2 same vector difference squared. So that appears for the x direction, y direction, and z direction. The summation should be made for I, difference, J difference, and K difference. Now we substitute, divide this one with the D, then we have the 2 additional power of D, and divide D to have the Burke modulus, attention per unit cross-sectional area. Thus we have introduced a D cube in the denominator. So to compensate that vector, we multiply D cube. Then actually the D cube is the volume element. And this is Burke modulus kappa. And this is indeed the gradient squared. Therefore, potential energy subtracted by kinetic energy subtracted by potential energy is a Lagrangian, and Lagrangian should be expressed in terms of a 3-dimensional integral for the Lagrangian density function. And that Lagrangian density function is 1/2 rho time derivative squared minus 1/2 kappa gradient squared. Again, note that this rho is the density per unit volume, and kappa is the Burke modulus, that means tension per unit cross-sectional area. Wait a second. Okay, we continue to consider the vibration of membrane, and we extend this idea to the 3-dimensional case. In 3 dimensions, the tension should be considered as a tension per unit cross-sectional area, and density should be considered as a volume mass density. And Lagrangian density function is written in this form. This is the 3-dimensional case. Rho and time derivative, partial time derivative of the field squared minus 1/2 kappa. Kappa is the Burke modulus, that is tension per unit cross-sectional area, and gradient squared. This here sum over I from that is running from 1 to 3 is also considered. Variation of Lagrangian can be made in terms of the partial derivative. Variation of Lagrangian due to the field itself is computed to the first order in variation of the phi as partial derivative of Lagrangian with respect to the field phi multiplied by the variation of the field. The second contribution is coming from the time derivative of the field, the Lagrangian density function partial derivative with respect to the time derivative of the field, and then multiplied by the variation of the time variation of the field. In addition, we have 3 contributions coming from the variation of the field with respect to the gradient. So the first component of the gradient of the field, we have derivative of the Lagrangian density function with respect to the first component of the derivative of the field, and second and third are considered, multiplied by the variation of the gradient. The first one is copied in here, and these are 2 pieces are reorganized to have the total derivative with respect to the time subtracted by the time derivative of the canonical momentum part multiplied the variation of the field. In a similar manner, we can also write down the contribution here, pull out the derivative, pull out the gradient outside, then it becomes, we have the partial derivative of the Lagrangian with respect to the gradient multiplied by the variation of the field, and then subtracted by the gradient operator applied to this vector. Alright, substituting this variation of the Lagrangian into the formula for the variation of the action. These 1, 2, 3 contributions appears in here. And we have 4 components that have the total derivative with respect to time, total derivative with respect to x, y, and z. Total derivative with respect to time can be integrated. The time integral can be evaluated completely, and we substitute the endpoints, the t equals t1 and t2 in here. The remaining integral is over x, y, and z. And the second one, we have derivative with respect to x, and x integral can be done completely. And then x integral is done, then we have left with the time, y, and z integrals. And after the x integral, we have endpoints x1, that is L and 0, lower bound and upper bound. The second contribution, derivative with respect to y, has the form. And remaining integral is integral over x, z, and t. And the last one, derivative with respect to z, is to be integrated out so that the remaining integral is over x, y, and t. As a result, these 4 pieces vanishes because endpoint values are all 0, because the variation is not allowed at endpoints of t, and endpoints of x, endpoints of y, endpoint of z. The variation of action is now completely reduced into the integral over time and space, whose integrand has a factor of variation. And this must vanish for any arbitrary variation delta phi. Therefore, we have an equation of motion. This is the Euler-Lagrange equation of motion for the wave propagating in the space, 3-dimensional space. We make use of this Lagrangian density function. We take the partial derivative with respect to field that vanishes. We take another derivative with respect to the time derivative of the field, that is rho times, by making use of chain rule, we find this. And then derivative with respect to the x derivative of phi brings in minus kappa gradient. Therefore, if I substitute these 3 results in here, this is vanishing. This is rho times the time derivative of field minus kappa times gradient summed over I. The gradient is to be applied to the divergence, then it's a Laplacian. Therefore, the final result is 1 over v squared, second order time derivative of field subtracted by the Laplacian phi equals 0, where v is the speed of the wave propagation, that is the square root kappa over rho. And the kappa is the tensor per unit cross-sectional area, and rho is the volume mass density per unit volume. We can now let us consider the canonical momentum and the Hamiltonian density of the system. Lagrangian density is expressed in this way, and then the canonical momentum density is the derivative of this time derivative of the field. It is called the canonical momentum density. First, let us recall how to construct a Hamiltonian out of Lagrangian. This single variable, single generalized coordinates dependent Lagrangian is written in here. Lagrangian is a kinetic energy subtracted by the potential energy, and we need to find out the canonical momentum. Canonical momentum is the derivative of the Lagrangian with respect to the time derivative of the generalized coordinate. In the non-relativistic theory, it should be mq dot. The Hamiltonian is obtained by making a Legendre transformation, that is canonical momentum multiplied by the velocity, subtracted by Lagrangian. Okay, we apply the similar method to find out the Hamiltonian density function. Lagrange density function is given here, 1/2 rho multiplied by the time derivative of the field squared minus 1/2 Berg modulus gradient squared. Canonical momentum can be obtained by taking the derivative of the Lagrangian density with respect to this q dot analog. Q dot analog is a time derivative of the field. Okay, substitute the time derivative of the field and multiplied by the canonical momentum subtracted by the Lagrangian density function is the Hamiltonian density function. Again, the Hamiltonian should be expressed in terms of the canonical momentum and its a conjugate relation, thus the generalized coordinate. They should be conjugate. In a similar manner, Hamiltonian density should also be expressed in terms of the canonical momentum density and the generalized coordinate, that is a field phi. Next, we consider the time derivative of Hamiltonian density function. Time derivative of Hamiltonian density function can be computed in this way. This time derivative is distributed in two ways, first vector and second vector. And the Lagrangian is copied in here. Time derivative of the Lagrangian should be computed in terms of the phi derivative and phi's time derivative. Phi dot's derivative and phi dot's time derivative. Phi is a gradient derivative multiplied by the gradient's time derivative. We notice that the canonical momentum is this one is the same as the canonical momentum. So these red pieces, they are completely canceling each other. We also find the equation of, we can just copy this first factor, the first term and second term in here. They both have a time derivative of the field, and then the last one is copied in here. We now make use of the equation of motion. We find the equation of motion is this form. Derivative of the Lagrangian with respect to the time derivative and the spatial derivative. And here, this one, this P is identical to this one. That is, we find this. Therefore, this one shows that this contribution is the same as this, because this is minus this. So if it moves to the right side, we find it is a negative value of this. This one, only this one remains. This one remains. If we compare these two terms, differentiation is made to the first vector, and differentiation is made to the second vector. So we can combine these two pieces into single one, derivative of single vector. Now, we find that this is a kind of divergence, II. This is a vector. So we introduce a vector SI, that is derivative of Lagrangian density function with respect to the gradient multiplied by the time derivative of the field. So substitute this one in here. We find this partial time derivative of Hamiltonian density is a minus divergence of the vector. Move this one to the left-hand side. We find that this is a kind of continuity equation. So there is some conservation law in here, hidden. Hamiltonian of a system can be computed by integrating the Hamiltonian density function over the space. Thus, the total time derivative of Hamiltonian should be evaluated as an integral over the space of the partial time derivative of Hamiltonian density function. As we already derived, the partial time derivative of the Hamiltonian density function is minus divergence of S, where S, each component of S is given in this way. We can further apply the divergence theorem to find out, to re-express this volume integral as a surface integral on the boundary. If there's, in that case, if this vector S decays, suppose that we have some volume of radius R, and the strength of this field S decays faster than 1 over R squared, then the area increases by proportional to the R squared, then finally this contribution vanishes completely as R goes to infinity, and then Hamiltonian is to be conserved quantity. All right, so we have just completed the all 14 chapters on the classical mechanics. We began with the elementary equation of motion, and we studied some calculus-based differential and integral approach. So the calculus, we have studied calculus that appears in the various problems in classical mechanics. And then we studied the matrix. Matrix is a kind of representation for the transformation rules. And various transformation, for example, rotation, and this is to be extended for the angular momentum as a generator of the rotational transformation. And we extended the method to find out the momentum is the generator of the translation, and Hamiltonian was the generator of the time evolution. All right, so if we consider the transformation rule, or especially for the inertial tensor that represent the rotation of a rigid body, we found that a symmetric, real symmetric matrix, that is actually the Hermitian matrix, was diagonalizable. Once the matrix was diagonalizable, then we were able to find out the principal axis. That means the eigenvectors. And all of the eigenvectors are orthogonal, and we have constructed the systematic way to construct the eigenvectors with unit normalization, and completed the theory to represent space in terms of a very useful and efficient, convenient basis vector that are called eigenvectors. The eigenvectors method can be used to deal with the rigid body's principal axis, and then it has been extended to consider a problem of oscillators. Once the oscillators are connected, the second differential equation was constructed as a very complicated way, that is a coupled differential equation. That method was applied to find out the components that are orthogonal. As a result, we have found normal modes that has a unique frequency, and as a result, the coupled system was found to be in a mathematical structure, found to be a linear combination of eigenvectors, and every eigenvector has a unique characteristic frequencies. The approach that we have is consistent with Lagrangian mechanics, and based on the Lagrangian mechanics, we were able to construct a method for the Hamiltonian mechanics. The Hamiltonian mechanics was also extended by making use of the Poisson bracket, the construction of the quantum mechanical theory. That approach used for the diagonalization was extended to the continuum limit to consider the vibration of a continuum loaded string. That was indeed found to be the same structure, a very similar structure as the quantum mechanical system for the infinite potential well. And then our Lagrangian mechanics was generalized into a continuum limit that represents the classical field theory. And classical field theory was used to derive the equation of motion that is consistent with the variation, the vibration of the string that completely satisfies the wave equation, classical wave equation. This approach can further be extended to consider the relativistic theory that deal with the particle and fields, that is called the quantum field theory. Although it was a very short time, you have started very hard to experience the basic building blocks of quantum mechanics, classical mechanics, and you have applied that method to study various fields of physics that includes quantum mechanics, electromagnetisms. And I hope you, equipped with these basic tools of classical mechanics, your study should be successful in the future. Good luck to your future. Thank you.